Hello everyone, my name is Chong Ma. I have been working with Metal Earth since 2019. The first project I worked on was a sturgeon transect. I was leading that project, and after about 2.5 years, I switched to another project called a Western Extension project. So that's the topic of today's presentation. Specifically, I'm going to talk about the structures and the kinematics of the Ridout deformation zone in the southern part of the Swayze greenstone belt, with some implications for the western extension of the Larder Lake-Cadillac deformation zone. So Bruno helped me in the fieldwork for a couple days. Special thanks to our friends in Ontario Geologic Survey who provided information for some of the outcrops. So here is the location of the Swayze greenstone belt, and that's the Ridout deformation zone. This presentation is part of the bigger project that's trying to understand the western extension of the two deformation zones here into the Swayze greenstone belt, Mitsubishi greenstone belt, and Mitsubishi greenstone belt. So I started with mapping the structures in this part of the Mitsubishi, then somewhere, right here, the Eagle River deformation zone and the Mitsubishi deformation zone in this greenstone belt, and lastly, this part of the Swayze greenstone belt. So today I'm going to show you some results from the Ridout deformation zone, and hopefully we can better understand the potential of the Larder Lake-Cadillac deformation zone. So next map is showing this location here. And the Swayze greenstone belt is considered to be the southwest extension of the RBTB greenstone belt. And to the north, we have this Nut River granitoid complex. To the east, we have this big Kinogamisi battles. Then to the south, we have Ramsey Algama granitoid complex. And to the west, we have this Kapskisin structure zone. So the stratigraphy here basically can be characterized as four volcanic groups from 2750 million years to 2695 million years, which are covered by this Ridout group. That's kind of like the youngest sedimentary unit covering the volcanic rocks. And these edges of the individual groups can be correlated to the corresponding assemblages from the RTB. Also, some 2670 million years alkalic volcanic rocks have been reported in the middle part of the belt, mostly along the Kente and Rondo deposits. The arcane intrusions in this belt range from 2750 to 2680. Then there are several gold deposits. That's mostly small, except for this Coty gold deposit, but this one is intrusion related. So I'm going to show you the detailed data collection from this particular spot of the belt. Here is an enlarged map. I collected data from those 5 locations. From west to east, we have this Mollard Road transect. That's where our Metal Earth R2 seismic survey was conducted. Then some data from the Nemax deposit and the Euro Road transect here. Then Highway 144 transect. Then lastly, this Londonderry Road transect. So first, I'm going to show you some representative volcanic rocks. The fail-safe volcanic rocks are dominated by different types of pyroclastic rocks. For example, this one, we can see fail-safe lapidistone and lapidituff intruded by some quartzmen, and all of them are flattened. And here we have fail-safe lapidituff interpreted with crystal tuff. Locally, we can see some Fannion to the north direction, so Yannion to the north. And here we see this quartz ferric crystal tuff. Then the mafic volcanic rocks are dominated by flows. They can be massive, they can be payload, they can be brushy. So here we have interlayered mafic flow in the darker area, and this kind of light color is the fail-safe. So I'm going to show you a detailed map along the highway. It's where you can see the best exposures, one of the best exposures. So here's the map. We can see the Navio Pluton to the north, then greenstone belt in the middle, then another Chester intrusive complex to the south. The fabrics are shown here represent the extent of the Ridout deformation zone. The different colors represent 2 deformation stages. So first, let's look at the data from the northern part of the deformation zone. 2 deformation stages are recorded in the rocks. The first one is pervasive, the subvertical foliation, ductile, with local exposed, preserved subvertical ductile lineation. This is the main fabric. And locally, we can see this kind of spaced faults. They can displace those quartz veins by dextrostractly faulting. And luckily, we found several outcrops showing the fault surface. Along the fault surface, we can see this kind of a ridging groove type of lineation, indicating the motion of this faulting. Then the steps here, they are consistently showing dextral motion, which is consistent with this kind of displacement of the quartz veins. So the second deformation can be characterized as dextrostractly faulting, locally overprinted the earlier fabric. Here is a summary of the data. The black lines represent the first stage fabric. You can see the foliations are steeply dipping to the south with subvertical lineation represented by the black dots. Then the red lines represent the second stage deformation. They are steeply dipping to the north with subhorizontal lineation. Let's jump to the south into the Chester intrusive complex. So we are going from the margins to the middle. Again, we can see 2 types of fabrics. Here we saw the boundary between the Ridout deformation zone and the non-foliated quartz porphyry of the Chester intrusive complex. So basically, you can touch the boundary, the southern boundary of the Ridout deformation zone along this transect. Again, you see those kind of pervasive fabrics of the S1 fabric, first deformation, and locally we can see the subvertical to steeply deep plunging ductile lineation. Then the second stage deformation is only locally preserved. We can also see the subhorizontal ductile lineation accompanied by those typical steps. Those steps are marked by quartz vein. So again, dextral motion. Here, the S1 fabrics are dipping to the opposite direction, steeply to the north. Again, subvertical ductile lineation. Then also subhorizontal crenulation, represented by the black triangles. They are correlated with the motion and the deformation of the first stage deformation. Then the red line represents the second stage deformation, and the lineation is represented by the red dots. As you can see here, it's subhorizontal. Then in this part, in the southern part of the deformation zone, I want to highlight one important feature of the Ridout deformation zone. Here we are looking at a cross-section along 2 stations here. So the left side is north, and the right side is south. same lithology, all quartz porphyry, different strain. So if we look at the bottom letters, so we have intensely foliated section here, then strongly foliated, then there's a massive fabric between, and strong foliated, massive fabric, strong foliated, massive fabrics, strong foliated. So you can see my point. Those highly strained zones, they are part of the same deformation zone, but they are spaced. You can have this kind of distribution of high strain fabrics at multiple locations in different types of deformation zones. But here is toward the margin of the deformation zone. This is a characteristic of this part of the deformation zone. In the middle part, it's continuous. Now let's look at the data from the greenstone belt itself. Especially in the fail-safe volcanic rocks, the fabrics are very well preserved. For example, here we can see, so right now we are looking at a vertical explorer here in this picture. We can see C-prime fabrics indicating north side up motion. So here is a shear band, that's the C-prime fabric. If we look at this part of the fault surface, we see the very well developed ductile lineation subvertically plunging. In the mythic volcanic rocks, we can observe some S0, so the original volcanic bedding, bounded by S1 fabrics. Then this SC fabrics and subhorizontal ductile lineation are pretty well preserved there, indicate dextral strike slip faulting. So the S1 fabric range from this orientation to this orientation, but they are all subvertical. The lineation I measured are all subvertical to steeply plunging. Then the second deformation stage, the fabrics are very intense. They are consistently dipping to the north with the subhorizontal lineations by the red dots. Now I'm going to show you the structural data summary of the Euro transect. Again, we see multiple deformation stages, including the first one. You can see steeply dipping S1 fabrics to the south mostly, and steeply to subvertical plunging ductile lineation. Then the triangles, that's the subhorizontal granulation, roughly perpendicular to the lineation. That's a relationship, they were coeval. Then the second deformation stage is characterized by spaced fault zones with a subhorizontal to shallowly plunging ductile lineation. So the motion is dextral strike slip rather than vertical motion along the fault surface for the first stage. Then we have subvertical granulation lineation. This has to be distinguished from the subvertical ductile lineation of the first stage. So it could be tricky. We were lucky to see some evidence for the third deformation stage, which has subvertical to steeply dipping foliation, basically similar to the fabrics of the first two deformation events. Then the ductile lineation is obliquely plunging, and the oblique granulation lineation I would say orthogonal to the ductile lineation here for the third stage. Now I'm going to show you the evidence for the third stage deformation, although it's rarely exposed, but we saw this. For example, here we see those SC fabrics, but if you pay attention, the S fabric here are filled with quartz. Those quartz are not crystallized, they are not deformed, they are the younger events. And here, so those are quartz gas veins. They formed by reactivation of the S1, S2 fabrics. Then we can see this oblique plunging ductile lineation associated with this latest deformation. The granulation of the last stage deformation is something like this, perpendicular to S3. Here is a summary of the relationships between 3 generations of ductile lineation from LS1 to 3, and the 3 generations of granulation from LC1 to LC3. So you can, if you go to the field, you can simply see those data can represent 6 generations of deformation. But here they actually represent 3 generations of deformation because each pair can be coupled. So here we can see the S1 foliation here on the surface. It's a vertical explorer, and the LS1 is pretty well exposed, and LC1 is roughly perpendicular to the ductile lineation. Then here we can see the LC2 granulates the older subhorizontal LC1. Then here we have LC1 being overprinted by LS3 and LC3, where you can see the LS3 and LC3, they are roughly perpendicular to each other. I found a oriented sample that shows LS1 subvertical, LC2 subvertical, and LS3 oblique. So this one and this one overprints LS1. Now we can look at the structural data summary from the other 3 locations. So the stage 1 deformation along this transect is mostly represented by the foliations, not very well explorers about lineation. Then the stage 2 deformation is shown by those subvertical foliation with basically horizontal lineation. Then in the Nemax deposit, the deformation was preserved in the conglomerating unit, the Ridout formation. The foliation is roughly east-west. You see the difference from the first transect to this transect here. The orientation of the foliation varies from location to location. But here we see the subhorizontal granulation represented by the triangles here. In the London Derry Road, that's the easternmost transect, we saw subvertical foliation dipping to the north with northwest plunging ductile lineation. We also saw the opposite, the opposite attitude. So some foliation dipping to the other way steeply with southeast plunging ductile lineation here. So this can be explained by folding, as the area was strongly shortened along north-south direction. Now I want to highlight some structures in the youngest unit, the conglomerated unit. Here we can see some beautiful SC fabrics indicating dextral shear. We are looking at the horizontal explorer. And the second one in the middle shows a dextral motion that produced shear bands. That's mythic clast, and we have fail-safe clast. Those are deformed in this way. Then we saw 2 generations of granulation lineation. So subvertical one of the second deformation, then the subhorizontal one of the first deformation event. They are preserved on the same foliation. To summarize the deformation of the conglomerate unit, we saw a lot of flattening of the pebbles, and that's the shortening along north-south direction. Associated with this flattening is this subhorizontal crenulation lineation. Then the second stage deformation is demonstrated by those SC fabrics indicating dextral motion. That's also include subvertical crenulation lineation. To summarize the structures in this area from the past summer, so the first stage deformation can be characterized as north-south shortening that produced subvertical foliation, subvertical to steeply dipping, plunging ductile lineation. So the structures that support this first stage deformation include IC fabrics on the horizontal surface, on the vertical surface here, and asymmetric structures indicating north side up motion, south side down motion. That's the secondary deformation component, but the major one is shortening, like a north-south shortening. Then on the horizontal surface, we can see a lot of boudinage quartz vein and folded, isoclinal folded quartz vein and some other isoclinal folds of the main fabric. S-fold and flattened volcanic clasts that includes the fractures perpendicular to the foliation. So they can be opened during the flattening process. Right now, those fractures are filled with quartz. Then the second deformation is characterized by dextral directly faulting that produce the subvertical foliation and subhorizontal ductile lineation, plus subvertical crenulation lineation in blue color here. Then on the horizontal surface, we can see rotated quartz veins and shear bands or C-pry fabric and Z-fold IC fabric here. We should be careful when we see this kind of asymmetric structures on the vertical surface that can be actually produced by the dextral directly faulting. If we just look at the vertical explorer, we can see, there are some vertical motions. But when I plot the IC fabrics on the StirNet, actually the motion direction is subhorizontal. So there's no apparent subvertical motion here. Rather, it's just the effects of the intersection of the explorer and the structures. Then lastly, the third stage deformation, oblique sinister faulting that produced the subvertical foliation, oblique ductile lineation. They basically reactivate the earlier fabrics and grow some quartz along the older IC fabrics. So now we can have quartz sketch vein. And also on the foliation, we can see random quartz aggregates. What about timing of deformation? So here we are looking at a horizontal explorer, the feldspar porphyry to the left, and the conglomerate, polymictic conglomerate to the right. That's the contact. You see a block of the conglomerate within the porphyry, and a block porphyry within the conglomerate. Then here yellow is a quartz vein that's not deformed. But the other two rocks are pervasively foliated. But if you look at the crystals in the porphyry, like this one here, they're perfectly euhedral. So no deformation at this scale, but at outcrop scale, they are foliated. So those foliation must be magmatic foliation. So the intrusion of this feldspar porphyry was in place, was during the deformation, so syntectonic intrusion. Then I look at the literature. There are 3 ages from this unit in the area. They are about 2680 million years. So the deformation was ongoing at this time. But we don't know when the deformation stopped, but at least we know it's ongoing at this time. Now, I want to draw your attention to those conglomerates. Right now, the literature describes it as temiskaming type sedimentary basin. And the major lithologies here are conglomerate, sandstone, and some minor siltstone. You can see the pictures here, typical polymictic pebbles, and they can be class supported, they can be matrix supported. The compositions of the class are very diverse, including tonalite, felsic to intermediate volcanic rocks, mafic volcanic rocks, and feldspar porphyry. Sometimes the feldspar porphyry can be a half-meter long, a big clast, that's strongly flattened. And airstone here, black chert, some jasper, some flattened airstone here, and gabbro, parrot, and so on. What about the timing of the deposition of this conglomerate unit? So here is a summary of the youngest zircons from the Mad Earth data provided by Russ. I'm sorry for that I somehow missed your last name, but it's Russ provided this diagram for considering the youngest geochemical zircon population in the conglomerate unit. Then I dig into the literature. Another similar age was provided, again 2680. Then if you still remember last slide about the age of the porphyry, 2680. So the timing of deposition is at this time, 2680. So the class composition, deposition age, and deformation history are consistent with the typical temiskaming type assemblage to the east. However, there is kind of apparent lacking of coeval alkalic magmatism. But remember, there are some alkalic volcanic rocks in the middle part of the greenstone belt there. So I personally think we can call this temiskaming basin, like basically the same basin, just a west extension of it from the Larder Lake area. As the basin is such long, it can vary in composition and maybe even the deposition environment. Lastly, I want to talk about the alteration in the high strain zone. So in the quartz porphyry, we saw quartz, anchorite, and feldspar as veins. In the felsic lapilli tuff, mostly it's just anchorite and ceracite. In the conglomerate, quartz, anchorite, ceracite, pyrite, and chlorite. So in summary, the structure data collected from past summer along multiple transects across the Ridout deformation zone demonstrate 3 deformation events after regional placement of the quartz veins that imply an earlier extension event. So we can have the boudinage quartz vein. The first event was characterized by north-south shortening that resulted in widespread subvertical foliation, subvertical to steep slick line. All of those are ductile. Subhorizontal crenulation lineation, boudinage and folded quartz veins, isoclinal and S-type folds, and north side up shear cyst indicators. The second event was also widespread in the region, characterized by dextral directly faulting that reactivated the first generation foliation and produced a subhorizontal slick line. Again, this slick line is ductile, and subvertical crenulation lineation with IC fabrics, shear bands, and Z-type folds. And the last one was minor and local, characterized by oblique sinister faulting that reactivated the first and second generation foliations and resulted in east plunging slick line, oblique crenulation, and new generation quartz vein. So the timing of the deformation, of the main deformation, is interpreted to be at 2680 million years old, based on the zircon from the syntectonic porphyry. The timing of the deposition of the conglomerate is also at this time. The deformation history, along with the Temiskaming type basin and high strain zone alteration, are consistent with those around the Larder Lake-Cadillac break to the east. So I think this the Ridout deformation zone is the west extension of the Larder Lake-Cadillac deformation zone. This is my personal opinion at this time. So if we look back at this regional map, not only the Ridout deformation zone, but also the Eagle River deformation zone here are structurally consistent with the Larder Lake-Cadillac deformation zone, although I have to consider the timing of deformation in the Eagle River deformation zone in the next couple months or 1 year. So perhaps we can continue the Larder Lake-Cadillac deformation zone this way somehow, all the way to Eagle River. I don't know, but I need to work on somewhere here in the middle to find more evidence if this interpretation is correct. And thank you very much for your time.